Last week we looked at nonlinear problems, so we wrote down variational problems and finite element problems in residual form. And we're going to do that again today, but we're going to use it for a slightly different purpose. We're going to use it to show how you actually impose Dirichlet boundary conditions in a rather nice and clean way. So if we remind ourselves a little bit of what we wrote down last time, what we said was that we could always write down a variational problem as find u in some suitable function space V such that f of u v equals 0 for all v in that function space. For current purposes will be purely Galerkin, and those will always be the same function space. And the way that we got this form from our original linear problem was we said, okay, so our original linear problem was the integral of grad u dot grad v dx equals the integral of some known function f times v dx. And all we did was a little bit of rearrangement where we move this over to one side, set that equal to 0, so that's now f. And we also last week showed that we can also then, using this more general form, write down nonlinear problems. And so for current purposes, we can keep in mind our linear problem. For the purposes of doing the boundary conditions, the linear problem case is sufficient, and we're very familiar with that one, so we'll mostly talk about that, but everything I'm going to write down is completely general. So now what do we want to do? We want to be able to impose strong boundary conditions. So remember from the first lectures that strong boundary conditions are the boundary conditions where we change the function space we're looking in to a function space which satisfies the boundary conditions. And that's the setup which is going on. And so we presume now, so this was an integral over omega, and we presume now that our domain omega has a boundary gamma, so we're not just solving on the surface of the sphere where the boundary is empty. And we assume that part of that boundary, which might be all of it, but some part of that boundary is a part over which we wish to set the value. So we wish to impose a boundary condition of the form u is some known function g of position x, and that's true on gamma d, which we will assume is some part of the boundary. So what we're now doing then is we're cutting our function space into effectively two parts. So at the moment we have some suitable function space over the whole domain, and we're searching for any function which is a solution in that space. And for current purposes, let's just think about the case where that's P1. It's a good mental model, but it doesn't matter which function space that is. So now what we've done is we've cut the world into two parts. We've cut it into the part which is on this part of the boundary, and there we don't want to search for a solution anymore, we want to say what it is. And the rest of the domain, where we do exactly as we did before, and we want to search for a solution. So what that means is we're going to write that V is V0 direct sum V gamma. Right, so what does that mean? It means that V is any function v in V is exactly the sum of a function in V0, which will be the whole rest of the domain where we're looking for a solution, plus a function which meets the boundary conditions on the boundary. And this is a direct sum, which means that those spaces are not overlapping. So it's exactly one part and the other part. And so this part of the domain, V0, is the space which is spanned by those basis functions in whatever basis we have for V, which vanish on gamma D. Right, so let's make this a little bit more concrete, and we'll draw a little two-dimensional domain, and we'll imagine that this part here is gamma D. That's where we want to impose our Dirichlet condition, and we've got some triangulation of this space. That's not a very good triangulation, that's a bit better. In all practical implementations, it will be a requirement that whichever chunk of the boundary you're using for a boundary condition, that coincides with mesh points. It's an incredible pain to do that in any other way, and since you normally control the mesh generation process to some extent, there's not really a lot of point in trying to do the hard problem. So now we have all of, that's our triangulation, and so we have a whole load of basis functions, right? So we have a basis function which is 1 here and sinks down to 0 over there. And that's part of the basis for the piecewise linear functions on this space. And that guy is going to be in V0, right? Because he vanishes to 0 on the boundary. And actually, even this guy, who's on a boundary element, he's in V0 because his value goes down to 0 at the edge. But this guy here, he doesn't vanish on the edge, right? He has a non-zero value over part of the edge. So he is going to be in V gamma, sorry. So now I've split up my space in these two ways, and that means that I can always then, if I have some function V which is in there, then that's always equal to a V0 which is in that one, plus, and in fact in this case, because it's an actual individual function, that's just a ordinary addition, plus a V gamma which is in that one. Hopefully that's so far nothing controversial or surprising. So we will then consistently use 0 and gamma whenever we want to talk about it. So if I write down a basis function phi, I meant a basis function, any random basis function of this guy. If I write down phi 0, and I'll write a superscript 0 because we already use subscripts of basis functions to enumerate basis functions. So if I write phi super 0, it means 1 in there, and phi super gamma is going to mean 1 over there. So we'll just use 0 and gamma all over the place to label things that live in these two spaces. So now what I'm going to do is we can actually, for a while, not think about the specific problem we wanted to solve, and we can go all the way back up to here. Now remember what we know about this. Remember what that semicolon means. That semicolon means is that this residual function might well be nonlinear in U. If we have a nonlinear PDE, it's going to be nonlinear in U. But it's always, always, always linear in V. It's a key requirement of the system. And the reason you know that is you got the weak form of the equation by multiplying by a test function. And you might then integrate by parts, but integrating by parts is a formal process, right? It doesn't change the meaning of the equation in some sense. It does change the meaning, but not in the sense of, that you would suddenly transform something which is linear in this argument into something non-linear in the argument, right? Integration by parts can't change that for you. So this guy is always linear, and that means that we can always write f of this part plus f of the boundary part. Okay, so I couldn't have, in the general case, split U up like this, because if f is not linear in U, then that transformation isn't true, right? That transformation is inherently what linearity means. But because f is linear in V, I can split that part up. And in terms of the practice of the finite element method, what does this mean? Well, remember that what we actually do is we solve this equation for each basis function of V, right? We do this for all the phi's in that position, and we use the linearity to say, well, if we got it for all the phi's, then we get it for all the other cases. And what's going on then is we can say, well, let's look at what we've done here then. So some of the rows of our equation system correspond to basis functions for the zero space, and some of the rows correspond to basis functions for the gamma space. So on some rows we're doing this one equals 0, and on some rows we're doing this one equals 0. And that's going to prove to be important, because what we need to do in order to solve the system with boundary conditions is get a slightly different set of equations by changing what we do on the boundary cases, and leaving largely what happens in the non-boundary cases on their own. So, if we have a boundary condition imposed, what does that mean? It means that we know the solution on the boundary. So we will no longer need to test with the boundary conditions test functions, right? That in the boundary boundary condition case, this one becomes moot. It's not a test we needed to do. Instead, we want to apply, because what this is saying is that the residual is 0 on the boundary. I don't care whether the residual is 0 on the boundary. What I care about is whether the boundary condition is fulfilled on the boundary. And then I need the residual to be 0 everywhere else. So what I can say is I'd like to get rid of this guy here, not bother with that, but replace it with another constraint. And the other constraint is going to be some sort of constraint, a new constraint, right? Not the same function, which imposes the boundary condition. So in order to understand how to write a constraint that imposes the boundary condition, let's remember what the residual is. So the residual is a function where if I plug in a solution in this slot, and I plug in any v in this slot, I get 0. And preferably, if I plug in something which isn't a solution here, in fact, by definition, if I plug something which isn't a solution in here, then for at least some v's in this position here, this will not produce 0. Right? That's all I need. Well, it's not quite all I need, because if we remember back to last week's lecture, in last week's lecture, the way we got to actually solve this problem was we differentiated this guy using a Gatto derivative so that we could use Newton's method. So having got a beautiful differential form, which in most circumstances that we care about is differentiable, and so this works for us, I really, really don't want to break that by introducing a non-differentiable function here. So I'd really love that to happen. So those are my constraints. I need it to be 0 in the cases where I've got a solution. So that means I want it to be 0 if U satisfies the boundary conditions. And I would like it to be non-zero for at least some test functions in the case where U doesn't satisfy the boundary conditions. So what we can do, remember that all of these functionals are completely prescribed by their behavior when I put a basis function in here. Because they're linear, it's good enough to describe the behavior for all the basis functions, because every other function is a linear combination of the basis function. So I can get back the behavior in all the other cases if I knew what it did when there was a basis function in there. So I'm going to define that f gamma on any U with any phi I, strictly speaking a phi I 0, because these guys are known, a phi I gamma, because these guys are known to come from the gamma part of the space, although actually you don't really need the gamma. You could define it extended everywhere if you really wanted to, because we're only ever going to apply it in the cases on the gamma, so we don't care. And so we're going to say that that is equal to ui minus gi. So what are ui and gi? So u is something which lives in the same function space V. So that means that u is equal to ui phi I over all I, or let's disambiguate and say uj phi j over all of those, with the same basis functions, right? And so ui is the coefficient of the ith basis function for this value of u. So in the P1 case, right, in the case where our nodes are point evaluation, that just means the function u evaluated at the node of this boundary condition basis function. Right, that's the simple case, but this is actually general. So if your nodes are component evaluation, because we're doing vector value function spaces, for example, then it's the same thing. It's the component of u at that point. It's the evaluation of the node. And so that's my value in here. And then gi is simply g evaluated at the node corresponding to this. So g could come from any space at all, but gi is g evaluated at that node. So what does this mean? Well, it means that if u takes the value of g everywhere on the Dirichlet boundary, then ui will be the same as gi. So that will be 0. And anywhere on the Dirichlet boundary where this does not apply, then this will be non-zero. So that's what we needed. This is a functional which does the job of being a 0 when we've got a solution, or this bit of the solution, and being non-zero when we don't have a solution. And also, it's really, really, really simple, right? That is infinitely differentiable. The derivative is really easy. Life is great. That's a nice functional to chuck in. In fact, the precise form of that is not coincidental. We get a really, really conveniently nice derivative, as we'll see in just a second. So that now means that I've got my new version. So this is my unconstrained version with no boundary conditions applied. And this is my constrained version. And what I'm going to do is I'm going to define that this is equal to f hat of u b. Right? So this is my new constrained residual function, which is just my original residual function on when v comes from the interior of the domain or the non-Dirichlet boundary, and it's my new version when v comes from the boundary. And because it's linear, you can take combinations. So you can test with a function which is non-zero both in the Dirichlet boundary and in the interior, and you get the sum, and that's just fine. For practical purposes, of course, we only ever test with the basis function, so you'll be in one of those or the other one. So far so good. So now we have a residual. And so now we need to think back to ourselves to what does that mean when we try and solve this system. Right? So now we're going to go back to what we did last week and try to generalize it to this particular case. So I'll take this stuff off here, back to this one, and I'll remind ourselves that we're now solving the problem with boundary conditions, the constrained boundary condition, boundary problem. And so what we're going to do is Newton's method, which we derived last week. So Newton's method is that my my next u is equal to, so this is not the u at the next time step, this is my next guess at what u is my current guess at what u is, minus J inverse Fu, where J inverse Fu is the Jacobian matrix which is given by the Gatto derivative. And we did the Gatto derivative last time, but I will write it up on the board because we need to think about what this does in our special part of the residual. So last week we learned what it does when we have a differential equation. We actually did some cases, but this week we need to think about what it does in the constraint part. So remember, what happens here is that df u tilde b is the limit as h approaches 0 of f hat u plus h u tilde b minus f of f hat of u v, all divided by h. And that is true for all v in V and also for all search directions u in V. I've probably walked off the screen there, but the last things that are out there are u and u tilde. And this gives us a way of defining the Jacobian matrix, which is the system we're going to solve, right? The way we get the Jacobian matrix, the system we're going to solve, is by putting the basis functions into here, and that gives us a basis for the system we solve it out. This is what we've done in previous lectures. So Jij, right? This matrix that we solve here to produce our update to our solution is equal to df of u, so still u, so it's still linearized about the current guess that we put in. That's sort of the point of these update methods. And then phi I, phi j. So now let's work out. We have we have our definition of f hat all the way through here. We have our definition of f hat on the boundary condition notes, right? So I'm not going to worry about what this derivative is if phi j is in the interior. That's not a problem because that's what we did last week. But we have the case where phi j is on the boundary and on the Dirichlet boundary. And so what happens in those circumstances? So this is now on those circumstances, remember, f hat of u phi gamma I is equal to ui minus gi. So what's the derivative of that with in the direction of the phi ith basis function of u? So, well, that's a constant term, so the derivative of that part's 0, and the derivative of this part is 1 for u tilde equal to phi I, and it's 0 if u tilde equals phi j not equal to I. So that's cute. Because what that means is that the part of the matrix which corresponds to the rows of the boundary basis functions, the boundary test functions, is going to be the identity matrix. So that's why we chose that form for the residual, because we knew its derivative would get us the identity matrix, which is going to make our life very easy in the solution process. So we can write this out. So what we want to do is we want to write out how the different blocks of this J matrix look. And I'm going to make a huge simplifying assumption now. I'm going to make the assumption that I've renumbered all of the boundary, all of the degrees of freedom, such that my Dirichlet boundary ones come first, so that I can just write out blocks. So there is no mathematical significance to that at all. Everything I'm going to write is true for any numbering you choose, but it's a lot easier to write up if you assume that you have all the Dirichlet conditions together and then all the others apart. So that means that I can write that means that I can write first of all, J00 ij, I'm going to call that the matrix which is the original Jij when both the test function and the trial function are in the non-Dirichlet boundary part of the domain. So these guys are those ones. And it's going to be 0 otherwise. And similarly, Jij 0 gamma, that's the one which is Jij when phi I is in the non-Dirichlet boundary part and phi j is in the Dirichlet boundary part. And 0 otherwise. And I'm similarly going to define J gamma 0, so that's the one where the trial function is on the boundary and the test function isn't. And J gamma gamma is the case where both the test function and the trial function are on the boundary. So what do we know? Well, we know that so J is effectively, so now I'm going to abuse notation a little bit. So in order to make various linear algebra operations well defined, I've defined these to be full-size matrices, right? They're all the size of all of J, which means I can do any operation I like on them. But they're also all only non-zero in one block of the matrix, right? So if I make this the, so I can write this out such that this corner is J gamma gamma, because J gamma gamma is going to be 0 everywhere else. And so then this block up here is going to be J gamma 0, and this block down here is going to be J0 gamma, and this block down here is going to be J0 0. So now we can ask ourselves something about what these are. And so what did we do? We changed F on the rows corresponding to the Dirichlet boundary condition basis functions. So that's these ones. This is where the actions happened. And these ones are going to be completely unchanged from the case where we didn't have a boundary condition. And what do these turn into? So the J gamma gamma block, that turns into the identity block. Right? One's on the diagonal, zeros everywhere else. And this one out here, that's going to be 0. That's the effect of those rules, right? So the rules we wrote down are unaffected by values. So the definition we wrote of the f gamma, of f on the boundary, didn't have any non-boundary values of u in it. So if it didn't have any non-boundary values of u in it, when you take its derivative with respect to non-boundary values of u, the derivative must be 0. It's unaffected by non-boundary values. It's only affected by the boundary values. Right? And so what's going on here then is this section is imposing the equation that that ui equals whatever I put on the right hand side. We'll see what that is. This section here is opposing the original equation away from the boundary. It really doesn't see the boundary. And this term here is the coupling. So this term here is the term by which the boundary values show up in the equations. Right? If that term was not there, then I could set the boundary conditions to any value I like, and that wouldn't change the solution on the interior of the domain, which would clearly be wrong and also very surprising. So, so how do we use this in Newton's method? Well, remember what we're doing in Newton's method. What we're doing in Newton's method is definition of we are solving J u hat equals the residual. It's the and because of this structure here, we know part of that solution already. Right? So what we know is that u hat I equals f u I I'm missing a v of that u. That's useful. I've just found a bug on the website. So actually it's not quite true, no. So what I write for fu here, so fu is a vector. So the ith entry of fu is f u I, right? That's the, and so no, so I was right the first time. So this is my vector that's here. The ith component of u is equal just to the residual evaluated if phi I is a boundary basis function. Right? That's all that's saying. So what I'm going to define in order to make myself able to write this is I'm going to define u hat gamma, and I'm going to define u hat gamma to be the vector, which is FUI for phi I in phi gamma, and 0 otherwise. So it's the part of the solution that I know already because of the structure of the matrix. So the reason why that's useful is because that means I know the solution variable. So remember, I'm solving this matrix times u hat equals. So I know this part of the solution. So now I can think back to the dim and distant parts of my undergraduate linear methods class, and I can realize that I can forward substitute to get this, the solution for this part of the matrix. Right, the effect, because all this does is adds j times this part of this matrix into these terms here. That's what that block does. So that means I can write my problem as J00 plus J gamma gamma. Right, so that's the diagonal blocks on this, and the off diagonal blocks of this are 0. Times u hat is equal to f of u minus J0 gamma u gamma. So now I've got a solution algorithm for my system, right? I've got a matrix times a vector equals a known vector on the other side, right? That's a vector, and that produces a vector. I can subtract them off each other. This is actually a really nice way of writing this problem, because we can see some important things about these, this equation, in particular about this matrix. So one of the important things about this matrix is it has 0 off-diagonal blocks. That means that any important symmetry properties that J had originally, the unconstrained J, I've kept. So if J was originally symmetric, this is symmetric. If J was skew symmetric, this is skew symmetric. If J was positive definite or positive semi-definite, this is positive semi-definite or positive definite. If J originally was diagonally dominant, this is diagonally dominant. So this means you can impose the strong Dirichlet boundary conditions without mucking with the symmetry of your original matrix. Some of the other mechanisms for imposing strong Dirichlet boundary conditions don't do that. Right? You end up with a non-symmetric matrix. It might be only a weakly non-symmetric matrix. So, for example, conjugate gradient might well still work, but you have lost something, whereas here you lose nothing. This is a perfect form. There's something else to realize, and the something else to realize is if you started your Newton solver with an initial guess for u which already satisfied the boundary conditions, then this would be 0. That's what it means if your initial guess for u already satisfies the boundary conditions, right? And so if this is 0, then this term is 0. So actually, you don't need to do this. Phi-direct doesn't do that, at least in the nonlinear case. What you can do instead, and what Phi-direct actually does, is when the user passes you in their nonlinear problem to solve, and they pass you in a solution vector, and you treat the current value of that solution vector as your initial guess, because there are lots of reasons why it might be a very good initial guess. For example, because we're solving a time-stepping problem and it's the solution at the last time step, which is a very good start for where we're going to be this time. So we treat it as the initial guess, but we don't use all of it. Before we start any of the Newton solver process, you change the initial guess values on the boundary condition nodes to the boundary condition values, because you knew how to solve that bit. And then that means that this goes away. And you can just solve this. So I've been now going for just about the requisite time, so I think I'll stop here, and after the break I'll give a few comments about how this is implemented, and then we'll start worrying about vector-valued function spaces.